Okay, so today's class is about invariance, mainly of what we call a Huber and Wiesel module. Let me give you some background. This is work that started 3 or 4 years ago, motivated by visual cortex in primates, so in humans, monkeys, where you have a set of visual areas from V1 to V2 to V4 here to the IT complex. That's what is called the ventral stream. V1 is here, back in your head, where information gets from the eye first, and then information goes forward towards more and more complex representations up to this region where object recognition happens. There are models of this, and it turns out that deep learning networks have exactly the structure of these models and were in fact suggested by some original idea of Huber and Wiesel, who found some of the basic cells in V1 in the 1960s at Harvard, got a Nobel Prize for it, and suggested in a very implicit way, in one sentence, the idea of this hierarchical architecture. In particular, after their suggestion, actually the original paper 59, there were quantitative models. And the first real quantitative models was by Fukushima, who was working at NTT Labs in Japan, the equivalent of Bell Labs, and several other models, more or less quantitative, of this idea that you have a set of layers in which you do first filtering operations, and then pooling for invariance, and then filtering and pooling and filtering and pooling. These first two layers in this model, which is these models we developed in about 15 years ago, and it's essentially similar to Fukushima, but closer to what we know about the physiology and the details of the ventral stream and its neurons. But in this model, these first two stages correspond to the simple and complex cells of Huber and Wiesel. Simple cells will be filters in different positions that are essentially oriented Gabor functions, like bar detectors, if you want, to a first approximation. And complex cells are pooling, for instance, with a max operation, choosing the simple cells among several in different positions with the same orientation selectivity, choosing the one which has the maximum value, is most active. And by doing this, you get same selectivity, so to an oriented bar, but you get invariance to position. These models work well. This was, for instance, this H-max model. If you have a test in humans, you ask, tell me whether one of these images contains an animal or not. The experiment is done in a similar way. There is an image which is presented very briefly, followed by a mask, another image, and then you measure performance, how well people are correct. And it turns out that overall people are 80% or so correct, and they are better at images where the animal is pretty large. They are worse at images where animals are far away. And the model, that model, does more or less the same as humans on this task. It's a feedforward model. This is the kind of situation in which you assume you have to assume these models work, in which you don't allow people to look at the image more than once, to change fixation, to move their eyes. And under this condition, you expect these feedforward models to work. And it's fair to compare to humans. And so these are under those conditions that this comparison is made. So they work well in terms of modeling human performance, and also many of the properties of neurons in the visual pathway. At least they model the feed-forward pathway. There are also feedbacks in the ventral stream from higher areas to lower areas, but that's for another time. And these models that are essentially the same architecture of filtering and pooling, with the difference that they are trained in a supervised way on a lot of labeled data, whereas the previous one is not trained in a supervised way. These models do very well, as you probably know. How many of you knows about ImageNet, the competition? Yeah. So ImageNet is this database of millions of images, thousands of object classes, and networks of this type have performed much better than previous systems on those kind of computer vision tasks in the last 3 years or so, really starting a kind of revolution in machine learning and related fields like computer vision and speech recognition. So the question is, why do they work so well? There is this field really needs a theory. Simulations are not enough. You need to know why. And so today and on Wednesday next week, I'm trying to tell you about the beginning of a theory, and today is about one stage of this networks. One stage of H max is not a hierarchy, but essentially one of the layer, and especially the invariance that you get out of a layer. So this is partly in what Lorenzo said last time. You have this in one layer of a network. You have several inputs that come from the image, like pixels, or from the layer before, with different weights. They get summated and then transformed through a nonlinearity that used to be a sigmoid, but in most of the recent networks is a ramp, or called rectified linear unit. So it's everything, the output of this nonlinearity is 0 for all values that are less than a threshold, and otherwise is a linear function. And after that, you typically pool, like in the Huber and Wiesel situation, in which there is a max operation over the inputs to these units here. And the result is that unit take the maximum values among its inputs. So this is the sequence of operation in one typical layer of a neural network. And I will speak mostly about what we call Huber-Wiesel modules in honor of Huber and Wiesel, in which we consider one of these cells. This could correspond to the complex cells of Huber and Wiesel, pooling over a certain number of its inputs. And in a typical, somewhat idealized deep learning networks, you have this series of layers, and each one doing these things, and we look at it as, you can look at it as a composition of functions. That's what Lorenz had mentioned last time. You can look at it as a composition of modules, and the kind of diagram I'll look, it's kind of an idealized version of what happens in several of these networks, and what happens in HMAX or similar model like Fukushima is that you have simple cells here, complex cells pooling over it. So you have here the linear combination, the nonlinearity, and the pooling. And this may be repeated several times in a layer, and then repeated in the next layer with these complex cells here, looking at this neural image produced by the activity of the complex cells. Okay. This is, the way it's drawn is a binary tree, but that's... okay, so this class is really about pooling and invariance. It's really about how one of these modules works and why, and trying to have a theory of this. This started, as I mentioned, 3 years ago, or 4 years ago, really trying to explain or give answers to some question about the ventral stream, the visual system, in terms of object recognition. What is really computing? What is going on there? What is the computational goal of this series of areas? And you know, what is really the computation that simple and complex cells are doing in mathematical terms and in terms of their properties? What can you prove? Related to this, in the recent 5 years, there has been a lot of data coming up from physiologists working on areas in IT that are tuned to faces, that are involved in recognition of faces. And one knows quite a bit about the properties of those cells, but one does not yet understand how it works. So part of the questions was trying to answer how this face system works. And there were other questions. For instance, our vision, and as in other primates, is strongly dependent on eccentricity. If I fixate right there, I don't see, I see something very blurred here, right? In fact, the density of the photoreceptors, the distance between them, these are like the photodiodes that measure light intensity in my eye, decreases linearly with distance from the center of the eye. Okay, so why is that? You know, is there a computational reason, or is just an accident of the system? Why this linear dependence on eccentricity? Okay, so these are questions that we'll answer today. Whether the answer is correct, there are various ways to say that. You know, one can ask whether it's biologically correct. One can ask whether it's mathematically correct. Mathematically, I think it is correct. Biologically, it has to be seen. These are kind of predictions for experiments. So today, as I said, will be invariance. Next week will be why are deep architecture with several levels better, more desirable than shallow ones with at most one hidden layer, so-called. So this will come next week. All right, so the idea about invariance and the ventral stream started with this hypothesis that maybe the main reason for this at least 3 or 4 stages of computation in the ventral stream, V1, V2, V4, and then IT, is to compute a representation of images that is invariant to usual transformations. Usual, I mean, when, for instance, I look at your face, I can come closer, and your face is the same, of course, but it's now much bigger in my eye, right? It's twice as big. The image is quite different. Or, if I move, it shifts. These are transformations. So translation, scale, and some rotation, and their combinations that happens all the time and make difficult to recognize the same object, because the same object can generate a lot of different images depending on the position and the distance and the angle of rotation. So the first step here is just to repeat what I was saying, is just a demonstration. It's very simple. That in fact, if you have an oracle, the idea is that the ventral stream is this oracle that could, for any image you get, it gives you a rectified version of it. So instead, your face will always come in the same position, at the same distance, at the same illumination and rotation, okay? Then, if this happens, the idea is that if there is an oracle that can do that, then the problem of learning to recognize your face versus other faces become much easier. And easier means I'll need much fewer labeled examples for training a classifier. So think of this stage of what the oracle does, what a ventral stream may be doing, as a pre-processing that simplifies the job of a classifier, like a kernel classifier or a linear classifier at the top. And here is one simple example. We used indeed the linear classifier on pixels. It's the simplest thing you can do. And you train the classifier to distinguish between cars and planes. And in this first case, the cars come in all orientation, distances, and sizes. Same for the planes. And I can train a classifier with 1 car and 1 plane, or 2 cars and 2 planes, or 3 cars and 3 planes, and then test on car and planes not seen before. And the performance remains a chance if I do this. Not surprising, because it's a linear classifier on pixels. But suppose I take the kind of images that an oracle could have given me. So they are all normalized to the same distance and scale and illumination. And I do now the training of the classifier. And now I get from just one example of a plane and one example of a car, I get better than 80% chance, right? So this is just to make the point that if I can get rid of these nuisance variables, so translation, scale, rotation, then the problem of learning becomes much easier for object recognition. And this can be quantified in a theorem that essentially takes a special case for translation in which you assume that you have an image which is d square pixel in size, and it may appear in any position in a window that is RD, so the image is, is d by d pixels. Okay, and the idea of how you can prove it, there are at least 3 different ways to prove this. The first one is an argument that says something like this. So the first one says, suppose that I need certain number of examples, say m examples, for achieving a good performance of the classifier when I present just the object. Okay, so there is no, it cannot translate or shift. It's just the object. Suppose I need m example to get an accuracy of 90%. Okay. Now I say, okay, same objects, but now they can appear anywhere in this bigger window. I can ask for each one of the m examples that are given, I could produce a number of virtual examples. This is the idea that in the literature on deep learning, they're also called data augmentation. I can, for each example, I generate a legal example without changing the identity of the same object, but translated. Because now this may happen. And so the obvious thing is, if I want to consider all possible translations where these objects can appear, I have now to have, for each example, R square virtual examples. So this will give me, if I have an invariant representation, I don't need to do this. So the gain I get is exactly this number of virtual examples. So that's one argument, one way to get a qualitative proof of this. Another one is to say, I know that the sample complexity of a linear classifier, so sample complexity, number of examples needed for a certain accuracy, is proportional to the log of the covering numbers of the space of, say, vectors that I'm considering. And the covering numbers is the number of balls of radius epsilon that I need to cover that space. So if the space, say, has radius r, this will be log of, thank you. This is how many balls of radius epsilon I need in a space of dimensionality d. So you see that sample complexity depends on the dimensionality of the space. So it depends, in this case, let's see, this would be d squared. The dimensionality of this original space is d square pixels. And this in the case of the bigger space, will become this square. So again, the ratio between the two is what I gain by having an invariant representation. A third way to show this that has the advantage of can be a bit more general is to represent the input to the classifier instead in terms of pixels. Suppose I represent the pattern here in terms of a Fourier series. So I have a function of f of xy, say x for simplicity, and I represent this as a sum from minus n half to n half of Cn. These are complex coefficient, e minus C omega, no, n, omega 0 x. And omega 0 should be something like 2 pi over d. I'm considering, for simplicity, let me consider just one dimension. So only translation in x now is allowed. Over there in the theorem is x and y. And so if I go from d to r time d, the number of coefficient I need goes from n to n time r. Okay, it's like you need to represent something here with a Fourier series. You need, say, the C1 will correspond to a sinusoid like this. But if I need to represent a pattern within this bigger window, I'll need this and all the smaller one, including these ones. So I need r time more coefficients, more sinusoids, exponentials, to represent a pattern that could be anywhere inside here. Okay. I was saying this is just for, I can do the same using the Fourier series. This argument also works if instead of translation, I now have, say, polar coordinates. Okay, where I can represent a pattern that rotates and expands around the center. And the same argument will work, so I can use it immediately for invariance to scale and rotations. Anyway, is that clear enough? So this is just to say that you can gain quite a bit by having an invariant representation. Now the question is how can you get an invariant representation? And before doing that, let me mention another reason why this is interesting. This question of invariance is interesting from the point of view of neuroscience. These were objects, 3D objects, like random paper clips that were used in some experiments with people, so psychophysics, where the task was to recognize one of these objects under different distances or rotations in 3D, and so on. And, and the same objects were also used in studying neurons in the monkey. And in particular, Nikos Logothetis, when he was at MIT and then Baylor in Dallas, trained a monkey to recognize several of these objects, about 10 or so specific paper clips, among others, right? So that the monkey knew this 10, it's like the monkey knew these 10 paper clips like 10 specific individual paper clips that were like 10 faces that the monkey knew very well, and all different positions and angle and viewpoints. So this is the example, for instance, of there is a paper clip up there, and the monkey was able to recognize among other paper clips with almost 100%. This is behavior, pushing buttons. And in the brain of the same monkey, there were, for instance, 3 neurons, 3 single cells, each one of which was tuned to a different view of the same paper clip. Like a grandmother cell dedicated to that view of that paper clip. And the same cells were quite selective. So here is one neuron, one of those, responding quite strongly to one view of that. This is the same paper clip, different views. That neuron responded with electrical activity strongly to that view, very little to different paper clips or different types of objects. But at the same time, this neuron, which was very, very selective, was quite invariant to scale. So the firing activity of this neuron remained about the same independently of, the size, the scale of this object. So there is this interesting question, how can a neuron be so invariant? And by the way, it was also invariant to translation, plus minus 2 degrees or so. How can a neuron be so invariant and so selective at the same time? So here is an algorithm which has the feature that is plausible from the point of view of what neurons can do. But before that, let me introduce briefly. How many of you know what groups are? Mathematical? Yes? Okay, almost everybody. So here are the basic properties for the objects G subscript I, which are the elements of a group. The product between them is also in the group. There is an inverse, and there is an identity. And for instance, you can imagine an element of the group, a rotation group in 2D, could be rotate by 20 degrees. And you can rotate by 20 degrees, and then if I apply again the same element of the group, it will rotate by another 20 degrees. Okay, that's one of the basic examples. I can do the same with translation and scale. In fact, the affine group in the plane, so speaking mostly about the plane because this XY is where images are, is the so-called affine group, which is, can imagine if you have a vector here which is xy, this matrix A is a 2 by 2 matrix, and this is a vector is a shift in x and y. So this is called the general linear group, the linear transform in 2D, general linear in 2D, and then you add to it the translations, and this is the affine group. And you get translations, rotations in the image plane, not in depth, and scaling, and all combination of rotation, translation, and scale, which are, for instance, shear and other deformations. Okay, so so this is, again, these are, when I say an element of the group G acts on the image, this means that is the image in which I've changed the coordinates through an affine transformations. Okay. Now, the algorithm itself does not need to know anything about groups, but in order to prove properties of it, we need to know about groups. That's why I introduced the groups. So the algorithm is quite simple. Let me describe it. So the little story here is so when you were a baby and you were in the crib and you were playing with the toys, one of the toys was a model of a bicycle. And playing with it, and looking at it, you see how it transforms. Okay, you know, you can move it further away, you can translate it, and you take a movie of this. Your brain does, and you store the movie, and that's all the learning you need to do in order to then have an invariant representation of other objects, any other objects, invariant to the transformations of this toy that you have recorded. Let me make the example in order to be simpler, and you will understand why, that the transformation when you're playing was just rotation. Okay, so you got a movie of, say, all the rotation, that don't need to be all of them, but suppose they're all of the rotations of this toy. You record them, you have a little movie in your brain, it has now 8 frames, and you store it forever. And when now you want to compute a representation of my face invariant to rotation, that will not change next time you see my face to be rotated, what you need to do is simply to take dot products of the new image, my face or the fish, with each one of the frame. Okay? And you get, these are dot products. I assume the images have the same dimensionality, same size. So each dot product gives you a number. You get 8 numbers. And I say this vector of 8 numbers, this, let's forget vector, this set of 8 numbers is invariant to rotation of my face. You'll get the same 8 numbers even if my face was rotated, okay? I'm not saying the sequence of the numbers is the same. I'm saying the set of numbers. And so in particular, the order does not matter, but the numbers do. Something like an histogram of this number that is independent of the order will not change. That's invariant. Yeah.
If the new image is in between,
yeah.
Then it is different.
Yes. I'm assuming that both my face and the bike can rotate only by, say, 10 degrees steps, okay? It's not a big deal because you can have more, and there is some limit at which 2 images are not different anymore, quantization, and but anyway. Okay. So let me just, so this is just one way to compute, say, an histogram. It's essentially counting, this is, TK is this bike, template, and GI are the different rotations of it. So, and this is a threshold. And so, and this is, say, a threshold, I would say, a step function, which is, say, 0 if this is below a certain threshold, and D, and 1 otherwise. So this is essentially counting how many times the dot product is larger than a certain number. And you do this for different n, so threshold. So this is really computing the histogram. Now, do you see why you have the same numbers? Anybody? Should be relatively easy in the case of rotation, right?
The dot product is invariant under rotation.
Sorry?
Because the dot product is invariant under rotation.
No, the dot product is not invariant under rotation, but the fact is that suppose I have let me see if I have a slide to show it more pictorially, but so there is a property of the dot product, maybe that's what you meant, is that this dot product is the same as this.
In space.
So I get the same dot product if so I have rotated the fish, but the template is like this, or I have the standard not rotated fish, and I rotate the template, right? And so when I do when I do this sum over all the rotated template, is like summating over all the rotated images for a fixed template. And since I have all possible rotation of the images, this will be independent of how the initial image is, how much rotated it is or not, because I will consider all of them anyway. Okay, so you can prove, more in general than this is invariant, and let me see. But here is again showing how it works. I can have, for instance, an object like the fish, and have different rotation of the fish, and they all give the same histogram. If I do the dot products and then take the histograms with, say, the bike template, and the cat gives me a different histogram, which is also invariant to the rotation of the cat. It's different, that's important, because the question is, if I do this, I get invariance. If I do this sum of all the GI I dot t, I get invariance, but do I preserve selectivity? The neurons were very selective, invariant and selective. This is another example, is rotation of the fish, rotation of the cat. This is translation of the fish, translation of the cat. So, okay, there are questions of invariance and selectivity. One way to address that is forget the templates for a moment and consider just the image of, say, my face and the rotations of it. So the first statement is that saying that these two objects are equivalent under the rotation group. So two images of my face, which if are only rotated, will qualify to be equivalent, is the same as saying that the probability of induced by a certain transformation, say rotations, the probabilities I get from all the images generated by a rotation of my face is equivalent to what is called an orbit. So the orbit generated by a group and corresponding to my face is the set of all faces that the rotation group in this case can generate. Okay? So it's just the set of all possible transformation under that group. And I'm saying that the orbits are equivalent to the probability distribution induced by the group of the image. So it's the probability of the image. This means that you can think of it as the probability that pixel 1 has this value, pixel 2 has this other value, and pixel 3, and so on, for all the 1 million pixels. It's a very high-dimensional object. But one way to think about it is that it will say there is this image with all these very specific values for each pixel, and then there is this other image, which is all these very values, and so on, right? So you can, it's really a list of all the images in the orbit. You can prove that they are exactly equivalent, but the intuition is that when you have a probability of images, which is really meant that you have a bin for every image, and you count it twice if you get exactly the same image. But if an image is different, the probability distribution will be different. So now orbits has an interesting, generated by a group, as this interesting property that they are unique. In the sense that, suppose I have an image of an object, and then I have another image, say, of a different object. And I generate an orbit from the first image, so all the images that can be generated by that one, for instance, by rotating and translating and scaling. There will be potentially an infinite set of images. Now, suppose that I have the similar orbit for a different object. suppose they touch or intersect, then they should be the same. Because I can generate every point of this orbit starting by this and acting on it with elements of the group. Okay? So two different objects which give rise to, if they act according to a group in 2D, they cannot intersect with any other object. So in 2D, and forgetting, this is the ideal case, because in practice you may have two objects that are different, but they may become very close to each other. So in practice, it may be difficult to distinguish with a certain resolution that they are different. But if you forget this question of discretization and errors, you have that orbits are unique, and of course, since each orbit contains all possible transformation under that group, they are invariant. So if I say that an orbit is equivalent to a probability distribution, then the probability distributions are have the same properties, that are unique and invariant. So this is a statement that if I is equivalent to I prime, in other words, what does that mean? It means that there exist, given an image I, there exists a G such that I is a transformation of this. So those are equivalent. They're one the transform of each other. And so this is the same if and only if I and I prime are equivalent to each other. And it's a bit more difficult to prove this, but this one, in this direction, that this implies, this is fairly simple, because you can notice that that if I have say a set A on which the probability associated with I and the probability associated with I prime is 0, this difference, so they are the same, then that means that two orbits intersect, and this means in turn that there exists a G prime is essentially the same as there, so that G I equal G prime I prime, and this implies I is equivalent to I prime. So we're not finished because what we had in that algorithm is not this high dimensional probability distribution, but is actually the probability histograms of P of the dot product of I and G I T. So the idea here is that you can represent a high dimensional probability distribution such as Pi, where, as I said, this could be the probability of x1, x2, x3, x 1 million, probability of an image, over, so a distribution induced by over all images generated by, for instance, a rotation. The idea is that I can represent these high dimensional objects in terms of a number of projections, so that I can represent this in terms of one-dimensional probability distribution that are the dot products of I and T. Several templates, like the bike. So these are numbers. So instead of having a probability of 1 million objects, I have a one-dimensional probability distribution, but many of them, depending for different k. And the result we have is that you can do this, and the number k you need is not too large, surprisingly. And let me introduce here one theorem that is actually not used in our proof, but gives you the idea, an idea of what is going on, and I will actually use in a different proof of this result here. So this is the Johnson-Lindenstrauss theorem or lemma or so, that is really at the center of what is called compressed sensing, which has been a very popular field in the area of signal processing, signal representation in the last 10 years or so. So this says the following. Suppose you have images, high-dimensional vectors, like vectors with 1 million components. So RD is a big space. You have n images there, small n. Two of them are U and V. And you can prove the following. This is what Johnson-Lindenstrauss proved, is that you can consider the distance between any two of those high-dimensional objects, L2 distance. And you can also consider projection of these high-dimensional images to a much smaller dimensional space, Rk, which essentially is done this way. The projection will be, you are taking this high-dimensional object, U, 1 million components, and you are operating on it with a matrix that has k rows but has n columns, so 1 million, you can think of each one of these rows as a random image. Really random, Gaussian noise. And you are doing the usual dot product here, and you are getting a vector in Rk with k components. And so this Pu is such a vector, and Pv is the corresponding one. So they are much smaller. But you can prove under certain conditions that the distance between this projected version of U and V is very similar to the distance of the original U and V. And this is true for all pairs of endpoints in Rd. This is called a quasi-isometry, quasi because of this epsilon here. And the interesting result is that the number k depends on some constant and depends on epsilon, but which depends on the constant depends on epsilon, but k does not depend on the dimensionality d. It depends on the log of the number of images you want to separate. Okay, and depends on them like the log, so it does not grow very quickly with the number of images. So this means you can represent this high-dimensional object in terms of much smaller projections of it. All right, so the result we have, let me skip to, is something similar in spirit, is that I'm not saying exactly what this is, but it says that I can replace this high-dimensional probability distribution with k dot products, with k histograms, one-dimensional histograms of the dot products with templates. So it's very similar in spirit and also in terms of the in the fact that the number of histograms, therefore of templates, like the bike, one is not enough, but the number of them to have uniqueness or quasi-uniqueness depends on the log of the number of objects that I want to distinguish. Okay, so one way to prove this is, which is not what the way we proved it. There are papers, by the way, if any one of you is interested, which are on our website. But what you can one way to understand how a proof could go is to use actually the Johnson-Lindenstrauss lemma. And so suppose you have n images, And for each of them, you have G transformations. So I have n images, and for each of them, I have G transformations. And so, according to Johnson-Lindenstrauss, I can represent each image, I can project each image which lives in RD. I can project it down to RK using K templates. Now, what I can do this, but now I also have for each of the templates also its G transformations. And so now I have a total of K times G templates. So the total number of K will be depending on log n. Sorry, let me say this way. Now I have n time G objects, images. And so the number of templates I will need for projecting will be in the order of log n plus log G. This would be, let's call it big K. And if I project in this space, I can then have a quasi-isometry, distinguish all of the images, including transformed of the original ones. This transforms of these original ones. And I can, in this case, take probability distribution, so essentially pool over the transformations if I don't care about the transformations, or pool over the different images if I'm interested in the transformation and not the identity. But this is one way to get results like this, which the way we got it, we use a theorem called the Cramer-Wald theorems that says that I can represent a high-dimensional probability distribution in terms of potentially an infinite number of projections of arbitrary random templates. So, an interesting consequence here is that you get invariance by pooling, and you don't lose uniqueness if you have enough templates. Okay, so, you know, the usual feeling by many people working with deep learning and HMAX in our case is that when you do pooling, you get invariance, but at the cost of losing that does not need to be the case if you have enough filters in this case, different filters. This corresponds to the templates. The other point that I may not have stressed enough is that that because of this property of groups and dot product, essentially you can move the G from here to here. So you can either, rotate the template, take the dot product, or you get the same number if you leave the template where it is and you rotate the image. Okay? So because of this property, which is mathematically trivial, but biologically is important, is because I don't need to have seen all the rotations of your face in order to be able to recognize a new rotation. I need to have seen all rotation of a template. And that allows me to get the same dot products that I would get if I have the fixed templates, one template, and I have all rotations of the image. And biologically and also in machine learning, sometimes a single image of a new object, like a face. You don't have multiple ones. But you can have a few specific templates, images, of which you have all transformation. That's okay. So this is essentially, you transfer learning or invariance from a set of images you have chosen to new images of which you see only one. That's the most interesting part of this. So the steps are that an orbit, so all the transformation of an object is fully characterized by this probability distribution over the orbit, if you want. And then instead of having the full probability distribution, high dimensions, you can have a set of one-dimensional probability distributions generated by dot products of I with a fixed set of templates. And then because of this property of the dot product, you don't need to see all the transformations of the image if you have all the transformations of the templates. Yep.
What properties does a template have to have?
In this, until now, basically none. They can be generic objects.
If it's zero, for instance?
No, yeah. They have generic in the sense that imagine you sample randomly an image from a large set of images. Could be any of them, right? Yeah. But I'll come in a second to some properties you may want. This says they work, not say that they are optimal in some sense. Okay, that's an open question. So, so basically the algorithm, as I said, the algorithm itself or its implementation in a visual system of a monkey does not need to know whether there is a group or not. As I said, that's something we need to know if we want to prove something. But so, memorize a set of images, which are templates, like the bike, and its transformations. And then that's the learning. Then at running time, you have a new image, never seen before, and you can generate a vector which is invariant to transformation by computing these dot products with these templates and computing, if you want, something like the histograms that are invariant. So again, it's you have an object, you have several filters, like simple, and are doing dot products with image, and they have different transformation of it. For instance, in the case of the simple cells of Hubel and Wiesel, transformation was translation. They are in different position. So you get different activity of these simple cells corresponding to the value of the dot product with the image. And then you have pooling and something corresponding to an histogram across different complex cells with different thresholds. And gives you, if you want, a vector, what we call signature, which is invariant, which represent the value of the cumulative histogram for different, essentially different bins of the histogram, different. So let me mention one of the motivation here was that one of the few things neurons can do are high-dimensional dot products. And that was a motivation for this algorithm for invariance. Neurons are very slow. Basically, nothing happens in a neuron faster than 1 millisecond, which is a kilohertz, which is amazingly slow compared to our computers. But unlike components of our computers, like transistor, which typically have 3 or 4 wires going in or out, neurons have like 10,000 in cortex. Connect are much higher. And what happens at the connection, you have a neuron here, the branches of the dendritic tree, and there are inputs coming from other neurons, and there are contact points, which are called synapses. And so you have various inputs, X1, X2. These are electrical signals. And a very simple approximation of what's going on at the synapse is that a number related to the voltage carried by this axon is multiplied by a weight, the strength of the synapse. And this gives rise to a depolarization in this postsynaptic neuron, which is proportional to the product of the weight of this synapse and the incoming signal. And then all these depolarizations from all these different inputs, 10,000, up to 10,000 of them, summated here, and this gives rise to activity of these neurons, for instance, different spikes. So what happens to a very first approximation is really a dot product. You know, it's product of the vector of x and t, each element, and then the sum of them. Okay, so that's why this algorithm could be easily implemented by neurons in cortex. This would be the dot product, simple cell with the input, a nonlinearity, and then the sum of them at the level of the complex cell. Yeah.
So besides the neuron, like does the dot product also store the template, or does it just see, like when you think about this, would you think about it as the neuron storing both the template and doing the dot product?
The template is the vector of the weights of the synapses. Okay. That's the template. Okay. This is, in the case of simple cells, they typically are like a Gabor function oriented, so something so-called the receptive field of a simple cell could be something like, for instance, like this. if you shine light here, you activate the cell. If you shine light, you inhibit. It's like saying there are weights that are negative and positive and negative around the x direction. And these are what are, each one is multiplied inputs from the photoreceptors, and the result of this is a number, which is the activity of these simple cells, which is going to be pulled from a complex cells higher up. Okay, so, and I'm not going to this, but possibility that simple and complex cells are just one cell. But that's, how many of you are physiologists or know about it? None? Okay, so I'll not say anything about it. Let me go to a couple of other things. One is, this looks awful, terrible. All the examples I made were with rotation. And the reason is the rotation group is the nicest one. Translation and scale are not as nice in the sense that they can go to infinity. You know, I can move, translate up forever. So rotation always comes back, is connect.
Even with rotation, like we still only recognize small rotation. Like if we turn your face upside down, it's harder.
Yeah, faces are a special case that we can discuss, right? We can discuss that. But in terms of the algorithm I described, it's not so so strange because, you know, typically of templates, we don't see all rotation, we'll see for the same reason. And there is a stronger argument for the case of faces. But so in the case of, what time is it?
27.
Yeah. So I think I'll stop in a minute. I'm just saying that in the case of translation and scale, you have to imagine that you are looking at what happens through a window. So for translation, it's simple. It will be just some part of the visual field. Does not go into minus infinity or plus infinity. It will go from minus A to B. It's essentially the pooling range of a complex cell or a unit in a deep learning network. There is a pooling range. That's the window, okay? And so the result basically of a theorem here says that you have invariance to translation for a subset of the window. Okay? And I'll show you next time that if you want to have simultaneous invariance to translation and scale, then the type of template that gives you maximum invariance to translation and to scale are Gabor functions. Okay. But every template will work. Here I'm just saying what is, you know, the one that gives you the maximum range, which you may not be interested. But okay, next time I'll finish the invariance part. I'll get into why more layers than just one or two. And that's very recent unpublished work that is interesting because that's one of the big questions in deep learning these days, to have some theoretical foundations for why they work.